Hola, buenas tardes. Mi español todavía no es bueno, okay? Lo siento in advance, so I will do this presentation in English. This will be a kind of an introductory level of thermal enhanced oil recovery lecture, okay? A short lecture. I will try to just give a kind of highlights about thermal enhanced oil recovery, and I hope you will like and you will enjoy it. So first of all, I would like to start with who I am, who is Berna Hascakir. By training, I'm an environmental engineer, and my Master of Science is also from environmental engineering. And then from the green side to the dark side, I started my PhD in petroleum and natural gas engineering. And all of my degrees are from Turkey. So I am Turkish. My postdoc is from Stanford University in energy resource engineering. And all of my experiences on related to petroleum engineering is on heavy oil and oil shale recovery by using electromagnetic steam, in-situ combustion, which covers all thermal enhanced oil recovery processes. I also work for Schlumberger as a senior heavy oil reservoir engineer, and I had a chance to work in Venezuela, Colombia. This is why my Spanish is muy poquito. And I worked also in UK, as you mentioned in the introductory portion. And right now I am a professor at A&M since 2012, and I am teaching reservoir and production engineering related classes. One of the classes that I'm teaching is thermal enhanced oil recovery as well. So I'm doing research on thermal enhanced oil recovery, asphalt precipitation, emulsion formation, emulsion mitigation, and produced water management. This portion is coming from my environmental engineering background. So before I will start going to the thermal EOR, I would like to give some introduction on why thermal EOR is our focus. Okay, so let's start with why we need petroleum really. So this figure is for United States, however, more or less the same for worldwide, which means that mainly we are consuming liquid petroleum for transportation purposes and gas petroleum mainly heating and electricity generation purposes in United States. And this figure is more or less the same worldwide as well. These numbers are more or less the same. And when I'm looking into this, I'm also seeing petrochemical industry that I'm consuming liquid or gas petroleum. So I would like to know more about that, why I need petroleum and how I am using it in my daily life. So this is the petroleum that petroleum engineers, we are producing. And then it is getting converted into gas and we are consuming it through transportation or through heating purposes. What else actually we are generating from petroleum? We are generating many things from petroleum. And not only petroleum is moving our cars, but also it is making our cars, okay? So the car interior is mostly made from petroleum. Wheels are made from petroleum. And roads are mainly made from petroleum as well. So if we can make our cars move, if we can make our cars produce, it is because of petroleum. And we are also converting petroleum in our daily life products a lot. In United States, we have using petroleum to as roofs, windows, doors, and also for as a cleaning supplies, we are using it. So if we can wash our hands right now, if we can protect ourselves from coronavirus, it is because of petroleum, because the best removal of the virus is accomplished by washing our hands properly by using soap, and soap is a petroleum product. And I have a makeup right now, I could make it because of petroleum. And in the morning I had a headache and I got a medicine, so it is because of petroleum again. So my clothes, this is made from petroleum. And most of the electronics you are seeing, plastic parts, are made from petroleum as well. So petroleum is making our life easy, making our life more comfortable, which means that petroleum is really very important for all of us. And we are using it in our daily life a lot. We are highly depending on it, which means that I would like to understand the consumption of petroleum more. So this figure on the y-axis, you are seeing world liquid fuels consumption in millions barrels per day. And the time scale is not in million years, okay? It is in the last 5 years. Before pandemic, as you can see, it was steadily increasing, and this is the forecast. And what we are seeing in 5 years, we have seen a kind of a 10 million barrel per day increase in our petroleum consumption. So which means that our energy need increases, and it will continue to increase when we return to our normal lives after this pandemic. But we know that petroleum is not a renewable resource. It is a finite source. And so if this is a finite source, and if we have already consumed most of the conventional oils, then what I would do, okay, finite source, then it is, we have already consumed most of the conventional resources that we can easily tap, that we can easily produce. Then what I will do right now, okay, I will start tapping unconventional resources. It's a great idea. Do we know what is unconventional really? And in general, what I'm hearing is unconventional because it is popular. Everybody is, instead of calling shale gas, shale oil, they are naming those resources just unconventional. And there is a misconception is going on, and we are just thinking unconventional resources are only limited to shale oil and shale gas resources. No, it is not true. We have a lot of unconventional oil. So shale oil and shale gas are unconventional because of the source rock. It has extremely low permeability, impermeable. Just the rock itself is making those resources unconventional. But the fluid itself can be unconventional. And the location of the field can be unconventional. In the Arctic, it is not really easy to produce oils. Okay, so the location can make the reservoir unconventional. The oil itself, the hydrocarbon that we are producing can be unconventional, and we will be reviewing those unconventional oils in a minute. And also the rock itself, reservoir rock can be unconventional, like impermeable, highly heterogeneous, and or highly fractured, okay? So those kind of things are making our lives not easy. That's why we are calling them unconventional, because the technology is still not sufficient enough to tap those reservoirs. Okay, so I would like to know more about the petroleum. Okay, I would like to learn how it formed in million years. I heard a lot that it's formed in million years, and it is in the porous rock, but how it came there. Okay, I would like to understand more about the voyage so I can digest and understand more about the unconventionals. So everything starts with organic matter decay. And okay, I'm organic matter. Unfortunately, you are organic matters, and dinosaurs were organic matters. And if you will die and we will start decay, then the first thing will come out methane. After that, we will start going under burial, and then this burial will continue, and it will cause an increase in temperature. And then first, this organic matter will turn into something that we are calling kerogen. Kerogen is the mother of petroleum. If you don't have kerogen, we don't have petroleum, okay? Every petroleum is formed with kerogen and from different type of kerogens. And based on the burial in the shale structure, if we are increasing the burial, the temperature will increase, and then, and again, these geologic times that we are talking about, it will happen in million years, then kerogen will turn into bitumen, and then bitumen will turn into extra heavy oil, then extra heavy oil will turn into heavy oil, and then it will turn into the oil that we are calling as conventional oil, and then we are producing it. or it will turn into gas, petroleum gas that we are producing. And everything happened in the source rock till now. Okay, we are in this impermeable rock, and we are calling it source rock, where petroleum formed. Okay, we formed the petroleum, and we didn't let it to seep away. Okay, it has taken a lot of years, million years in geologic time, and after it's formed, it will start to expand, and it cannot fit anymore in the source rock, and it will start seeping away. We are not waiting till that moment, and we are tapping those reservoirs in the United States right now that we are calling oil shales, or shale oil or shale gas. Okay, and you are seeing the major shale oil and shale gas reservoir locations here in the United States. So those are based on the kerogen type, can be ended up with a gas reservoir, can be ended up with oil reservoir, or can be ended up both gas and oil reservoir. Okay, or if it is like kerogen type 4, it can end up with nothing. Okay. And okay, so I'm trying to define here unconventionals, and the first unconventional I define by using how petroleum formed. And let's go through the other unconventionals. We are not limited to shale oil and shale gas, and they are not the only unconventional resources. What else we have? Okay, so this oil and gas couldn't fit anymore inside the impermeable source rock, and it will start causing some cracks in the shale source rock, and then it will seep away. While it is seeping away, it needs to find a cap rock, and then it can accumulate at the bottom of it, so we can form the regular petroleum reservoirs. So it is seeping away, but it cannot find this proper cap rock, and during the migration, it is losing its light components. Okay, and then it is forming heavy oil, extra heavy oil, and bitumen reservoirs, which means that they are already lost their light components. And we are calling those resources as well unconventional, even though they are staying in a kind of a permeable rock. But because these oil resources have extremely high viscosities, then we are calling them unconventional as well. Okay, I talk about something viscosity. I would like to go into details about the viscosity because it is very important for thermal enhanced oil recovery processes. So we are doing categorization of the crude oils, the naming of the crude oils based on their viscosity at reservoir temperature and the API gravity at standard condition. So API gravity is always measured at standard condition, okay? At standard condition. So we have a kind of an oil flowing limit, which is 10,000 centipoise. If my oil resource, if my hydrocarbon resource has an oil viscosity more than 10,000 centipoise at reservoir condition, I am not looking into API gravity, and I'm calling them bitumen. According to this graph, I have a lot of bitumen in Canada, okay? Very high viscosities. I have also bitumen resources in the United States, Venezuela. I have also some in China as well, okay, bitumen resources. And below oil flowing limit, first of all, if you would like to just visualize what is bitumen, ketchup-like, okay, peanut butter-like, chocolate-like, something that we are trying to recover from the reservoir. It is extremely difficult, okay? And because this is solid, okay? Chocolate is solid almost. Peanut butter as well, it's almost solid. And if you would like to do the categorization below 10,000 centipoise, that categorization that we are doing based on API gravity. Okay. Anything at standard condition heavier than water is called extra heavy oil. And you are seeing here that we know if we would just put water and oil in a glass, we know that oil will stay at the top and water will stay at the bottom. And because of the density difference, oil is less dense than water. But the situation for extra heavy oil is vice versa. Water is at the top, extra heavy oil is at the bottom, because the density of extra heavy oil is more than water density. Okay, so this is how I'm doing the categorization for extra heavy. And for water, API gravity is 10 at standard condition, and less than 10 is defining my extra heavy oil. What about heavy oil? In between 10 and 20. And what I'm seeing here, Venezuela has heavy oil, extra heavy oil. China has a lot of heavy oil resources as well. And I have India, Indonesia, but these are not limited to those countries. We place some of the countries here. Okay, let's go back to our unconventional question. We said shale gas and shale oil are unconventional. Heavy oil, extra heavy oil, bitumen are unconventional because of the viscosity. And I have another resource that I can call also unconventional. This time it is not shale oil, but oil shale. Okay, what's the difference? So while petroleum is forming, we are starting from here and going all the way down here to form shale oil and shale gas. But in geologic times are still continuing. Okay, still the world itself is producing petroleum, but it will take million years again. Okay, and if the voyage stopped here in the Carrigan level, then I'm forming my oil shale reservoirs. Okay, so I could come till here, but I couldn't go after that because I need more time. I need million years to do that. Okay, still, and they look like this rock. And as you can see here, the darker spaces, darkest places, they are Carrigan. And what I'm extracting from this one, this is solid. I'm extracting from this hydrocarbon a synthetic oil. Okay, I'm extracting synthetic oil. So what I'm doing, I'm speeding up this process in the as an in-situ method, and I'm converting Carrigan into oil and gas immediately by applying proper heat. So I'm not waiting for a million years. And we have a lot of resources as well on Earth, and the biggest resources in the United States in Green River, but Estonia is producing a lot from Carrigan. And we have in the Green River region one company which is Estonian based, also they are producing synthetic oil. Okay, so I talk a lot about unconventional, how they formed. Okay, so they are tough reservoirs. They are not easy reservoir. That's why we are calling them unconventional, not conventional. It's unconventional. So why I'm talking that much? Is it worth to talk that much? Is it worth to learn a lot about unconventional? Let's check it, okay? In order to understand that, I need to understand the reserve and I need to compare it with the conventional resources. So this is the conventional resource. It's around 1 trillion barrel left behind. And when I'm looking into heavy oil and bitumen, 10 times more than what we are defining as conventional. But this is proven reserve, which means that there are some other reserves that we will prove in the future maybe. Okay, and these are the locations of those reserves. According to this map, I can see that Canada, Venezuela, Middle East has really significant amount of heavy oil and bitumen. So this is their main driving mechanism in the economy. Okay, and what else for the? We said oil shale is also unconventional. I would like to know more about the reserve. It is 3 times more than the conventional resources. So I am trying to still squeeze conventionals and trying to get more and more oil out from conventional. and I'm just thinking about if it is worth to do research on heavy oil and oil shale. And these reserves, projected reserves, are showing me that, yeah, they deserve to do more research on them, so I can use them as future petroleum sources. Okay, then what is the problem? Why I'm not tapping this till now? What was the really main reason making those resources unconventional? So with the heavy oil and bitumen, the main concern is their high viscosity. And with the oil shale, I have two concerns. First of all, the hydrocarbon that I'm trying to extract from these resources are solid. Okay, these are kerogen. I'm talking about kerogen, and kerogen is inside the low permeability, almost impermeable rock. Okay, this is our source rock. It in million years, it will host also oil and gas. So this is a tough reservoir rock and tough hydrocarbon as well. So I would like to know more about the viscosity. So these animations are showing me why viscosity is a barrier in front of me. And this is honey, and honey viscosity is 40, for this example, let's say 40,000 centipoise. And I have also water you are seeing. So viscosity is a kind of a measure to resistance to flow. And as you can see, water is flowing readily and easily when compared to honey. And I am not dealing with even honey-like structures. I'm dealing with something really tough to recover. Okay, this is an oil sample from Venezuela. This is an extra heavy oil sample, and this is an example for light oil. So how I can solve this issue related to high viscosity? I know that as a scientist, I know that viscosity is highly sensitive to temperature. Not only heavy oil, but also bitumen is also very sensitive to temperature. If I'm increasing a little bit the temperature, their viscosity reduction is significant. Okay, so I can use this to enhance the mobility of these oils in the reservoir. So I will apply Texas heat or Mexican heat. This way we can just recover those oils more effectively by increasing their mobilities, by reducing their viscosities. And how I am doing it in petroleum engineering? By applying thermal enhanced oil recovery methods. And I'm teaching at A&M EOR, Thermal EOR, and we are doing all of these studies in the laboratory as well. So we are capable to do all thermal and non-thermal EOR processes in a lab scale. So let's go into more details about thermal enhanced oil recovery. And we have hot water flooding, steam flooding, air flooding, electrical heating, and electromagnetic heating. And we will go into details all of these in a minute. And these are some abbreviations, but I will go through all of them in this presentation. So what makes oil move in any thermal enhanced oil recovery? First of all, I'm enhancing the mobility by introducing heat into reservoir. That means that alteration of viscosity due to introduction of heat is making oil move. Apart from that, okay, we reviewed that there are a lot of petroleum products, right? One of them is like cleaning supplies. Like I said, soap is a petroleum product, and detergents are petroleum products. And detergents are actually surfactants. And also, while we are trying to remove oily grease materials on our pan or on the stove top, what we are using another petroleum product that we are calling them solvent. And solvent is solving that oil in your hands, in your in the kitchen, everywhere. So they are all petroleum products, and in EOR processes, we are injecting those under the ground to recover oil, and we are calling them solvent flooding or miscible flooding, and we are calling it surfactant flooding, chemical flooding. During thermal EOR, because we are altering oil chemistry, we are generating those surfactants and solvents in situ. Yeah, because what we need petroleum to produce those things, and we need a refinery, and our refinery is thermal EOR method, because we are applying really high temperatures, and then we are generating surfactants and solvents inside the reservoir in some certain thermal enhanced oil recovery processes. That's why phase behavior is also driving the oil from injection well to production well. So we are creating solvent bank, we are creating some other banks inside the reservoir. Those banks are moving the oil to production well. Apart from that, if I'm using elevated temperatures, like in in-situ combustion, like in electrical heating, like in electromagnetic heating, I am cracking the oil and I am generating a new hydrocarbon inside the reservoir. And those things are called as chemical reactions. And those chemical reactions are also pushing my oil to the production well. So I am applying thermal enhanced oil recovery to unconventional oil that I set as like extra heavy oil and bitumen. Apart from that, I can apply thermal EOR also to conventional oil after the primary recovery methods, after the secondary primary recovery methods. When I reach the oil, maximum oil production, and oil started to decline, but I am 100% sure there are a lot of oil left behind, then I can switch back to thermal EOR, and I can apply also thermal EOR to conventional oil reservoirs. So let's examine one by one each thermal EOR. Hot water flooding, steam flooding, air flooding. Anything with flooding means that I need 2 minimum wells to accomplish that flooding. I will use the first as injection of hot water, steam or air, and the other well I will use it to produce the oil that I displaced by pushing it through thermal enhanced oil recovery. And when I am coming cyclic steam stimulation, I need just one well, okay? And I will use that well for steam injection, then I will shut it for soaking for a period of time, then I will reopen that one, but this time not for injection, but the production purposes. So just one well is used for injection and production purposes at the time. So it has 3 different stages. This process has 3 different stages. So why I'm calling it not cyclic steam injection, but cyclic steam stimulation, because it is effective near wellbore only, okay? What I'm looking for, if I'm looking for something near wellbore, then I'm calling it stimulation method, okay? And if you will visit a cyclic steam stimulation, the kind of an oil field that are using cyclic steam stimulation method, then you are seeing a lot of wells in the field, and every well is working with 3 stages, and they are close to each other because it is a stimulation technique and it is only effective near wellbore. In order to sweep the entire reservoir, you need to place a lot of wells in the oil field. And when we come to SAGD, which is steam-assisted gravity drainage, you need 2 wells, but their orientations are horizontal. The top well is for steam injection and the bottom well is for bitumen production. And you're forming a steam chamber, and then around the steam chamber, the oil is flowing to the production well. So I have 3 different steam processes, and I didn't understand really why I had those things. So the answer is easy. The reason is based on the viscosity, their effectiveness are changing. Steam flooding is effective for lighter to heavy oils, okay? And if we are treating extra heavy oils, steam flooding may not respond very well. Therefore, we need to switch to a stimulation technique, which is cyclic steam stimulation, because in this technique, steam will spend more time with extra heavy oil, and it will provide the necessary time for extra heavy oil to reduce its viscosity in a flowable range. And when we come to SAGD, we are looking for higher viscosity, solid-like structure like bitumen, because bitumen requires more time to spend with heat as well, and the steam chamber that we are growing during SAGD is giving that opportunity to bitumen. So it is staying with bitumen, the steam is staying with bitumen sufficient time and reducing its viscosity effectively. And the other thermal EOR method is in-situ combustion. Again, I need minimum 2 wells to make it happen. It doesn't mean that I am open to have like 10 wells. You can have as much, but you have to have minimum 2 wells in order to call it in-situ combustion. Otherwise, you can name it with other names that you can provide. And what are the differences between these three? So forward combustion. In forward combustion, we are placing the heater in the injection location, and we are injecting air from injection location. In in-situ combustion, I can inject air, which is the cheapest oxidant, or I can, if I have money, I can inject more expensive oxidants like pure oxygen, which might be dangerous, but you can inject it as well. So you need an oxidant to inject through the injection well. Heater location is also at the injection well location. And what about reverse in-situ combustion? Injection location the same. Heater location is going to the production well location. And what about this? Another abbreviation, it is high pressure air injection. High pressure air injection is applied to light oils. So methane is a light oil, CH4, okay, or propane is light oil, C3H8, okay, and these are extremely difficult to ignite oils because they are light oil, they are extremely stable. They don't want to break down their atoms, and they don't want to separate from its hydrogen atoms. And because the ignition temperature for those hydrocarbons are extremely high, which is making in-situ combustion process is extremely unfeasible. So how we are finding a way to ignite them? By increasing pressure. If I can increase the pressure of those reservoirs, then the ignition temperature is dropping. It is PVT, which means pressure temperature volume relation. And this way I can just reduce to necessary temperature to ignite those light hydrocarbons in the reservoir effectively. And when we come to electrical heating, it is another stimulation method like cyclic steam stimulation, which means that it is effective near wellbore. Near wellbore means in situ methods. And we can also apply it as an ex situ method, which means I can mine the reservoir if it is mineable, okay, like oil sands in Canada are mineable, like oil shale in Utah, mineable, you can mine them, and you can heat it up those reservoirs in a process center by using electrical heating, and you can get it done more effectively at the surface. And the last and the craziest thermal EOR method is electromagnetic heating, and we have several publications. Actually, we have a lot of publications on each thermal enhanced oil recovery processes. If you are wondering, you can go to my website under publication. You can reach many of them. And this is our electromagnetic wave spectrum. And for you to visualize the height of those waves, I am providing here some figures. As petroleum engineers in my electromagnetic wave spectrum, I'm interested in this region, radio frequency and the microwave region I'm interested in. which means that lower frequency and higher wavelength region I'm interested in. And this is the craziest thermal enhanced oil recovery. And then I would like to just give a kind of a quick overview of all thermal enhanced oil recovery methods. Hot water injection is the simplest version of thermal EOR. It's extremely easy to apply, and if you can do calculation by using a calculator, you will not get surprises. Whatever you will calculate as oil production, you will get exactly that oil production. It's the simplest. We know a lot about hot water, and also we know a lot about steam. It's easy to apply and reliable. Reliable means what? If I'm projecting that I will recover 20% of the oil, I will recover for sure 20% of the oil in place, okay? So I know the basics a lot because I have a lot of applications in the field. So I have a lot of learnings for hot water and steam injection. However, those processes, even though they are easy to apply, reliable, it comes with some challenges like greenhouse gas emissions, excessive water use. So they have some environmental impact, and they are really significant environmental impacts. And what in general the oil industry is doing, they are injecting, along with the steam, some other chemicals that we are calling solvent, surfactant, to reduce the environmental impact of steam and still produce the same amount of oil through that they were producing through any steam processes. Because of those challenges and because of the low oil recoveries, as thermal EOR experts, I might call myself one of them, we are seeing as future combustion and electromagnetic heating. And I will come in a minute why I'm thinking like that, okay? So why in-situ combustion and electromagnetic heating are future thermal EOR? We will start with in-situ combustion, and I will give a kind of a daily life example for you to understand, digest what is in-situ combustion really. Cigarette example is the best example to understand in-situ combustion, because whatever is happening in a burning cigarette is happening in the same way at reservoir condition, okay? So here, my reservoir is tobacco, okay? And I need to inject an enhanced oil recovery, thermal enhanced oil recovery fluid, which is air. And this is my injection well location, and this is my production well location. And I'm trying to sweep the tobacco from here, which is a solid hydrocarbon. And then at the end, I am producing gases and tar, which is getting accumulated in the smoker's lung, okay? So what's happening is amazing during in-situ combustion. So we are burning tobacco and turning some ash in the reservoir. And it's happening in the same way in the reservoir. So these are the impurities inside the crude oil. So for crude oil, we are always calling them hydrocarbon. However, crude oil has sulfur in it, oxygen in it, okay, nitrogen in it, heavy metals in it, because I'm an organic matter. If I will decay, I have my bones contain significant amount of calcium. In my veins, I have blood and it has significant amount of iron in it. So how I can just think I'm just hydrogen and carbon? I'm not just hydrogen and carbon, and I'm made from mostly water. Even water molecule has a lot of oxygen, and I'm inhaling a lot of air. So every organic matter which is going through decay has also oxygen, nitrogen, sulfur, and heavy metals, and the other metals as well. So I cannot separate them. The process of petroleum is making them interact million years, and through in-situ combustion, these unwanted impurities inside hydrocarbon molecule is getting deposited in the ash form. It's because of what? Because of the combustion region that I created by burning this tobacco. And I'm reaching at around the same temperature in the reservoir, and this temperature I'm reaching this temperature because of the formation of this coke zone. This coke zone is carbon-rich residue, and once it is meeting with air at high temperature, it is creating an exothermic reaction, and this exothermic reaction generates huge amount of heat. So you cannot touch by your bare hand this zone, but it is amazing that you can touch here. Just a few millimeters away from this hot zone, you can touch it. How it is possible? Because of the magic of chemical reactions. Chemical reactions are consuming this extreme heat immediately, which is making this process very amazing and very complicated. And why combustion is really the future? Because this is my initial bitumen before combustion, and this is my oil sand mixture before combustion. And after the combustion, I am producing something really with extremely low viscosity, and I am doing primary refinery on this oil in situ by leaving behind most of the impurities, unwanted products. Okay, I can sell this product easier than this product. And when I'm checking the reservoir rock after combustion, what I'm seeing clean sand. Okay, I am sweeping everything inside the reservoir if combustion can reach those regions as well. So I am producing oil which is more mobile than initial oil and contains less impurities than the initial oil. This is why it is future actually. And also, in-situ combustion can be applied to wide variety reservoir, deep, shallow, okay, thin, thick, whatever you would like to apply, not like steam. And when we come to the electromagnetic heating, I'm interested in this region, radio frequency microwave region, in where I am interested in long wavelength and low frequency. Why I'm interested in that crazy method? Because when I'm comparing with conventional heating takes a lot of time. But in microwave heating, so you are achieving what you would like to do immediately. Like you have a piece of food that you would like to heat it up with a conventional oven or microwave heating. With microwave heating, couple of minutes, less than a minute sometimes, sufficient enough to heat it up the entire food. But with the oven, first of all, you need to heat it up and you need to bring it a kind of a sufficient temperature. Then at least 10-15 minutes, you need to heat it up your food. That's why this is the first reason, energy efficiency. And the second reason is it is giving volumetric heating, not conductive heating. So it is heating up the entire reservoir instead of like heating portion of the reservoir. That portion of the reservoir heating is heating beside rocks and it continues like that. No, it's not happening this way in the microwave heating. That's why it seems like it's really promising. So when you look at which method that we would like to apply to our specific reservoirs, we can see a lot of screening criteria in the literature. And we did for cyclic steam, for steam flooding, for in-situ combustion, which reservoirs are feasible, which reservoirs are not feasible based on the existing experiences. But it doesn't mean that these are the only limiting parameters. So this is saying, let's say, reservoir depth is very critical for steam and steam flooding, and this is the only true screening criteria, because you cannot generate steam beneath these depths because of the pressure limitation. So you will be in supercritical region, but you cannot generate steam at that condition. And when we are looking into porosity, let's say more than 25%, it doesn't mean that if your reservoir has 20% porosity, it will not work in your reservoir. It may work as well. These are just favorable favorable parameters. So how I can understand really? Screening criteria tables are helping me, but not giving me the exact answer if a specific thermal EOR is my method to try in the field or not. So while we are looking into favorable factors, we are seeing a lot of favorable factors for different thermal enhanced oil recovery methods. But in general, what we recommend is really, we recommend if you would like to apply thermal EOR, you should start from laboratory, okay? A laboratory start means that, first of all, if it is a flooding, you need to try it in one-dimensional setups. If it's something like SAGD or cyclic steam, we have proper design setups for those purposes because it should be 2D. And in the cyclic steam, we need to have one injection well, and it needs to stimulate around the well. So everything should start in the laboratory. Then what we need to do in the laboratory also as well, we are recommending to go to 3D, 3 dimensions. And you're seeing here one 3-dimensional setup, and this is my laboratory. And after you tried and tested a thermal EOR in the laboratory, and after you model your laboratory results, then you can start upscaling your laboratory results to field. And then you can go into the pilot test, and you should model your pilot test, and then you need to do the field modeling, and finally you can do the full field application of thermal enhanced oil recovery. So if you are wondering more information about those methods, you can find a lot of information in my website under research. And this is all I would like to mention about thermal EOR. I'm like 1 minute late, I believe. Thank you for your attention. And I'm opening the floor for questions.